All right, I guess you can hear me. So I'm the Ralph Foster side of this talk here, and we're going to talk about the methods and technologies abstracts that we received. So how do I get the PowerPoint showing on the screen here? Great, thank you. And advance it with the arrow key. Okay. All right. Yeah, that looks all right. So the primary theme that we got, or the workshop goals that we had, were to review the state of the art in the SAR-based geophysical parameter retrievals, identify knowledge gaps, deficiencies, identify distinct needs for validation, and to propose novel approaches for advancing scientific research. And when we sorted through all the abstracts that were assigned to us, what we quickly figured out is that they were all novel, and they were almost all employing some method of machine learning or otherwise exploiting large numbers of images. And that's important because machine learning requires large amounts of data for training and validation. And that's an important thing because the other aspect that we were supposed to review was what was the biggest difference between the 2003 meeting and the 2023 meeting. And I did a little bit of thinking about it, and a little bit of computation, and I came up with a number of about 1 kilo per year. But I don't think that's what Johnny was really looking for. And what it actually is that back in 2003, SAR images were incredibly expensive for normal researchers, especially non-European researchers. And that was a huge barrier to advancing basic research. So, learning SAR data is very challenging. And if you only have a few images, it's very hard to get moving. And if you wrote a proposal to get some money to do some research, you would have to justify this enormous image cost to a program manager, which from experience I know was very hit or miss. So I wanted to show 2 examples of the impact of the adoption by ESA, starting with Sentinel-1, of a free and open data policy. And so the 2 examples I want to look at are research into tropical cyclones, hurricanes, typhoons, etc., and just the application of machine learning. So for tropical cyclones, SAR provides this ultra high resolution surface wind stress vectors. And the current standard of using SAR tropical cyclone imagery is essentially treating it as a glorified wide swath SFMR. So you're just getting the wind as a function of position. But there are more complex applications that you can come up with that are going to require a lot more data for studying. And then the second is just this generic issue of machine learning, which is a rapidly expanding research area overall in meteorology and oceanography. So what I did was I searched the database for published papers and conference proceedings with keywords. It was either tropical cyclones or typhoons or hurricanes, and then RadarSat and RadarSat-2, et cetera, going through the different SARs that have been out there. And there were several milestones of tropical cyclone research with SAR. And the first is the Canadian Space Agency started this Hurricane Watch program where they collected all the possible RadarSat-1 images of tropical cyclones. But those data were held in Canada and they weren't widely shared. They were barely shared at all. Then in 2008, CSA put out an announcement of opportunity towards the end of RadarSat's life, saying that we will give you free access to our archive of 160 tropical cyclone eyes. And that coincided with a major field program, experiment program by the Office of Naval Research on the impact of typhoons on the Pacific. And one of the important goals of ITOP was to get quantitative about how to use SAR imagery on tropical cyclone research. And the pre-planning for the field program coincided with the CSA announcement of opportunity. And then during the program, ONR purchased a large quantity of ITOP SAR eyes, coinciding with all the research programs. We had aircraft, ships, buoys, all kinds of data. And then the next big milestone was Sentinel-1 and the SHO, I've been calling it the SHOC, I guess it's called SHOC, in which they're capturing as many tropical cyclone images as possible. And they've also picked up the RadarSat-2 and RCM. And so this is just publications by year, a count of publications by year. And I think it's relatively clear that even after CSA was collecting tropical cyclone eyes, they were having no impact on the literature. A few papers scattered out here and there came out, no big impact. Then they released the data, made it public, gave a couple of years for people to work on it, plus ITOP, and you can see this impulse response of papers appearing in the literature. And SAR is starting to have an impact on tropical cyclone research. And then you see the explosion with Sentinel-1, free and open data, boom. It's become a cottage industry. So this is the impact of free and open data on basic research. And this is one example from ITOP. There were collected this super typhoon Meji. It hit the Philippines at a category 5 super typhoon. There were, I think, 12 or more images tracking it across the Pacific. And this is to compare to the recent one of Hurricane Freddie, I think it is, going across the Pacific. But it was done back in 2010. So the other example is just machine learning. And due to commercial applications, machine learning has been this growing field overall, and it has now diffused into basic research in meteorology and oceanography. And I say if you look at the number of papers published per year in any meteorological or oceanographic application, that to me looks like exponential growth. And that means you're in the linear phase of an instability process. It is growing, it's growing without bound. There's no restrictions on it. We haven't reached saturation. All right, so now you look at machine learning applied to SAR. And this is anything, not meteorology, not oceanography, any application of SAR and machine learning. And what I see is that SAR was sitting at the kids' table at the big family dinner, drinking fruit punch, while the adults in the room were having a great grand party. And then all of a sudden, free and open data, boom. So this is an important thing, is that to non-Europeans, which is, or people without ready access to SAR, it was very difficult. It was very hard to get SAR data to do any research. And I think this is one of the most important differences between 2003 and 2023. And I really wanted to make that point very, very strongly that for non-Europeans, I think we just owe a thank you to ESA for the free and open SAR data policy. So from here, Justin is going to.
Okay, so continuing on, I'm going to summarize the abstracts that we received slides from and try to summarize those quickly. And again, we have the breakout session to go through those a little bit more. So I'll try to be brief with these. So this was just starting from the contribution of David Arthurs, which really just echoes the point Ralph so poignantly made, is that open data is key. And another aspect here that I really want to drive home is the reproducibility of science. And he took this graphic here from Wikipedia, just showing that there's this cyclic cycle with everything being open. And that's what's really important to, improve our research capacity. Okay, this next submission here is from Muriel at ESA, and this was just an overview of the level 2 Sentinel-1 products. So we did hear a little bit about this this week already, but I felt like it was strong to highlight a couple points from this submission. There's ongoing work at ESA with the inversion of the geophysical models. Also, there's deep learning applications with the significant wave height, and then the quasi-linear approach to swell retrievals, or the spectra from the level 2 product. So here are some knowledge gap or deficiencies. So I'm not going to go through all of them, but just highlight a few. So there's been a lot of work with the cross-pole, especially related to high winds, and I think Ralph will talk about that a little bit later. There's issues with denoising. This is particularly true for the cross-pole, and there is some work need to be done still on the co-pole as well. There's no spectral measurements right now over TOPS modes, so this is ongoing work that ESA is trying to do to get spectra out of these imagery. And there's also no joint, swell, current, or other inversion. And this is probably another, I guess, dimension of the synergy approach by actually trying to make these algorithms exchange information. So I think that's a promising topic of research. So even though it's mentioned here as a knowledge gap, this is also an opportunity to improve. And then also, typically what we're doing now is single measurement retrieval, right? You use one imagery and you calculate your parameters from that image, but we can do better. And I think using multiple images in close proximity, you can actually help the algorithm improve. So that's another, I think, promising technique. So this next slide here shows a classification using the IW mode here in the Mediterranean. And this shows the different color codes here on the left images. This is just a quick look. And then on the right of these two examples here, it shows the color code shows these different phenomenon that I briefly gave an intro on yesterday, but it shows the spatial distribution and regional patterns for that. And I think this is something that could be really promising in the future, is actually using these classification part as almost like a first filter to then basically flag or maybe even be used in the next algorithms, the more parameter-based algorithms we've been using for years. So that's probably a nice opportunity there. So planned approaches, improve in denoising, geophysical model, especially with the radar sat and cross-pole, is ongoing research. There's planned improvements also with the radial velocity measurements. And then I did skip the middle one there, but the intra and inter-burst cross-spectral from TOPS and SLC also is ongoing work. So the next two submissions are actually related to Harmony. And I'll just be brief on these. This first one here is very technical and related to how you actually simulate these data from Harmony. And the approach here, and what's novel about this, I guess, is that you follow through on the math. I'll just highlight some of the key points, is that in the bottom right here, this bistatic view, the equation has actually changed. So it's not a hyperbolic problem anymore. So we need a new technique to solve this issue. And the solution then that these authors propose, just jumping ahead a little bit, is this spectral extension method, that they're able to actually get a unique mapping. And I'll just be brief on this one, but let's talk about this more in the breakout if there's any questions about that. And then the next submission is from a similar group here. And this is really looking forward now to the Harmony mission. This is actually simulating some data for the Harmony mission. And I want to highlight just one figure I found very interesting. So really, they're doing an end-to-end performance simulator for Harmony. And that needs to be done, right, with to prep for the mission. And I'll just go to the last example here, which I thought was very interesting to highlight. This is the full simulation then of what the data might look like. And if you see the zoom in here, this looks really clean, right? This is probably even cleaner than what we have from Sentinel now. So it looks like this data holds a lot of promise. So those first three contributions, which we labeled here, were more of the technical approaches. And now the next set of abstracts are more, it's technical, but it also has some geophysical application. So that's just how we broke it down. So this next one is from Martin Gade, using SAR data to monitor coastal erosion and morphodynamics in intertidal areas. And I think this is very important topic just because it's been shown in literature many times that these intertidal areas are key, right, for preventing damage to nearshore areas in coastal zones. So what these folks did here is they're just stressing the importance of understanding this area. Okay. So there's a need in this area to do frequent monitoring of the location. And also this area is highly cloud covered. So SAR is a great technology then to monitor the area. And what they did was they use a convolutional neural network. I won't go through the details.
We'll get you a new one.
Okay. So this is the original SAR image and then a binary. So we'll go over to the next one. This is detection edges. And then you can make these binary maps. And then what's really fascinating then in application is that you can look at differences between, this is here spring 2017 and then spring 2020, and then the difference. Thank you. So you can see these high details then in this coastal area. So I think that's a really nice application of machine learning and the SAR imagery for this problem. And I also like to point out too that when a lot of the discussions Ralph and I had were, I mean, most of this meeting, right, is all about methodology. But I think this section in particular, its uniqueness is maybe new applications of SAR, or also there's a lot of theme of machine learning and statistical approaches. So okay, so I'll go through this, skip this, but this is the convolutional neural network approach that these folks used. And I'll move on to the next one, which is MEDI-SAR, which is an exhaustive augmented data set of segmented Sentinel-1 SAR ocean observations of the Mediterranean Sea and Black Sea. And this contribution here is really robust in the fact that it used every IW image in the Mediterranean Sea. And I think this is going to be a growing trend in the field to really use a lot of these data. So before we start, one point I wanted to add about this slide is that this team at least recognizes this, that these problems are very interdisciplinary, right? So you need folks that have the expertise in geophysics, data science, and even the remote sensing aspects. And this team has all that, and I think that's a really important point to make as well. And even in my own research, I've been working a lot with data scientists, and it takes a little bit of effort actually to communicate with what you as the geophysicist wants, or the remote sensing wants, and what they can do and what the tool is they have, because they have very sophisticated tools now, but really this communication is key. So that's one point I really wanted to echo about this contribution here. So this is the data coverage that they have in the Mediterranean Sea. On the top right plot, and then on the bottom right plot, this is the amount of observations per month. So you can see there's quite a few imagery that they were able to analyze, 12,000 images per month, and they use the whole archive. So I'll just highlight a few examples here. This first one, so the backscatter image on the top left there, that's the co-polarization channel. The next one over, so top middle panel here, this shows the slick detection. So these are using a machine learning algorithm. This is the detection of the different slicks. And then now the synergy then with the chlorophyll, you can see the other product on the top right, and you see there's a lot of resemblance between the two patterns. And I think moving forward to a good idea that we can do is once we're really comfortable with our SAR methodology and the machine learning detection, you can actually start even looking more at the maybe deficits of on the other side. In other words, start actually looking at the chlorophyll and learning from both technologies. The bottom two plots here show a climatological approach then. So using all the data, this is the occurrence then or number of slicks detected in these regions on the bottom left from SAR, and then from on the bottom right there, this shows the chlorophyll concentration map. So you can see there are a lot of similarities, but there's also some differences. So it's pretty interesting. The next example here is rainfall. So this is the copolarization channel top left, and then this is the segmentation of this particular image here with rainfall. On the bottom panels, this shows the quick look image there on the bottom left, and then the middle one, this is the convection. So microscale convection, and this is a heat map of that. And then the bottom right there, this shows now the brightness temperature from a different technology to show the agreement between them. So I'll just go, there's a couple other examples that they have in this contribution, but I think you get the flavor of what they can do with this type of approach. So the next contribution is from Lauren Hoffman, and this is machine learning for understanding changes and drivers of variability in sea ice motion. I think that was brought up in the Synergy session yesterday about how you can use machine learning. Well, this is one contribution that does so. So on the left-hand side, this is a physics-based model. So you can see there's a lot of coupling between all these different systems here, and I'm not going to go through those details. But then on the right, this is the machine learning approach. So what they do is the inputs are the present day wind velocity, your previous day ice velocity, so vectors, U and V components, and then also your previous day ice concentration. And then you can use a convolutional neural network then to predict the output of the ice velocity present day. So that's what these folks do. And this next slide, they're able to show the improvement that this has using convolutional neural networks. So on the left, this is the correlation coefficient between the ice velocity and comparing it to the convolutional neural network. So if it's a high number, that's a good agreement between the model and the observation. And then on the right, this is actually comparing the previous approach, which was more of a linear regression model, to the convolutional neural network. So when it increases, that's an improvement in the correlation coefficient. So you can see most of the area is red, but there are some areas here of blue. And my interpretation of this is probably this is a different, maybe different physics in these areas. So that's one way you can interpret these results. So I think that's, I'll just go to the next one then. So before we move on, looking forward on this work, they're very interested to use SWOT in the future. This would add more information. So also be always forward looking with your research. So it's great that this team mentioned that. The next contribution was from ship wake detection from Bjorn. And he's using many different satellites here. So TerraSAR, Cosmo, Sentinel-1, RadarSat. And I'll just quickly summarize these results. So he first breaks down the different features of the ship wakes that we can see. So these divergent waves, these V wake arm, this turbulent wake, traverse waves, ship-generated internal waves, and even the Kelvin wake arm. And some of the knowledge gaps, so he did a pretty extensive literature review. I'm not going to go through all of them, but one of them here is C-band. And the rare comparison with X-band radar. And then also the fact that the slant range is typically not considered in the literature. So they used this approach here where they were able to basically isolate all these different contributions and how that will impact the detectability of ship wakes. And they summarized this in this nice table here. So it's color coded with green being a new finding and then red being a deviation from the literature. So I'll just highlight a few. Maybe I'll start with the X-band versus C-band. So if there's an increase or an up arrow, that means that there's an improved detectability in the wake of the ship. So comparing C-band versus X-band, you can see that there is an improved detectability in X-band, and that, I guess, is contrary to the literature. And you can see all the different other contributions. After reviewing this in more detail, this seems very similar to what we expect from looking at a lot of these imagery, so it's nice to see that it's actually quantified in such detail. So that was it for the contributions that we received, and for those folks who didn't submit slides, you're certainly welcome to contribute, so please do. I'll just move on now, and I'll give it to Ralph in a second to bring us home. But I just wanted to give a little bit of introduction, I guess, on the 2 points Ralph opened with, which was a case study in the boundary layer dynamics, and then also with also talking about tropical cyclones. So when I was in the group with BREST for several years during a postdoc, and when I first went there, I was looking a lot at wave climate, and this plot here on the upper right was just a quick thing I did one afternoon, and I was looking at this is a PDF of the ocean surface wavelength just over July for all these different years across the platforms. And I was very curious to see that Sentinel here shows out very different than the other PDFs. And we were scratching our heads for a long time about this. So this was right when they switched from, or were implementing the methods they had for NVSAT to Sentinel-1. They didn't do many changes right off the bat. So they basically used the same method. And what was happening is that the Sentinel images for these wave mode images, they have higher resolution, less speckle, and they have, most importantly, a larger footprint. So this larger footprint allows a lot of these other things, and this is the what I would briefly describe yesterday. There's other things in these imagery that actually were making noise in the methods. So that's, I believe, what we were seeing there with that PDF plot. So this is work from Chen Wang, who did his PhD with the group in Ifremer and BREST. And these are 10 different classifications that we came up with collectively that we regularly see in SAR imagery. So I'll just go through these first 3. Let me see so these first 3, so people can see online. This first one here is lack of atmospheric variability. So there's just really ocean waves across the scene. You see no large scale structure. And just to remind everyone, these are 20 by 20 kilometer imagery. This next one here show these, not sure where the mouse went. Okay, these long striations really, and these are roll vortices in the lower atmosphere that are creating these patterns. The next one over is overturning in the atmosphere related to convection in panel C. And A, B, and C here, just these alone, these are pretty ubiquitous signals. So that if you grab any random image, we haven't been able to put an exact number on that, but we think it's probably above 90% that you're going to see one of these. So really, the atmosphere is dominating these imagery. And I won't go through the rest of these. So we've been using detection methods to basically classify those imagery for more geophysical application related to the boundary layer. And we've tried many years since the one publication in 2019 to improve, and we haven't been that successful yet, but we think it's a function of the training data set, which is really important, and that's maybe something we overlooked on the first run through. So there's been a theme, I think, this week of talking a lot about validation data sets. And with machine learning approaches, at some point, like the machine learning, I think, will be just as good as what you train it on, or that's what you can hope, right? If you have a really good method. So I really want to stress or emphasize the fact that your training data set is extremely important. And we've been finding out this in the last year that you need to make sure that it's unbiased relative to your true population. Maybe sounds trivial, but it is something to consider. And in this slide here, I wanted to show an approach that we've been doing lately. Typically in machine learning, you can download these, Google puts these, for example, ImageNet is a popular one you can just download from Google. And this is, the source data is actually a lot of different imagery that were developed to make basically the structure, the convolutional layers are already built on those data, right? And those may not be representative of what you really want to classify. So you can actually go a little bit further and you can train your model here specifically on that imagery. So this top one here, this is typically fine tuning. So then when you want to, for example, detect SAR imagery, really you're just retraining or putting weights on all these different connectivity here in these convolutional layers. But you can just go a step further and actually train your model all on your source data. So this is a little bit of expensive calculation, but it does seem to pay off in the end. And you can train it completely on SAR data. So I'll just hand over here to Ralph, who will take us home then, doing a couple case studies here, looking at stratification or using these different imagery to do some geophysics, and then also with cyclones.
All right, yeah, thank you. I wanted to just step back real quick to these 10 image classes here. And I encourage everybody in this room to vie for the world championship of the capability of SAR scientists studying the ocean to actually identify the features in the SAR image correctly. And I think that if you're going to be a world-class SAR oceanographer, SAR meteorologist, you need to be able to look at the SAR images and know what you're looking at. So I strongly encourage everybody to join in the challenge, vie for the title of world champion, and receive a glorious prize. So when I got back into SAR, working with this wave mode data was right around the time that Justin had figured out that Justin and Chen and the other folks at IFRIMER had figured out that you could really see the boundary layer in these wave mode SAR images. And so we, Doug Vandemark, Justin and I wrote a proposal to go in and start analyzing these data. And Chen Wan was already there doing some research. He built this preliminary retrained inception V3 model, CM wave, we call it, to identify these SAR features. And there were issues with it, but what we knew for a fact was that it had a very low false positive rate. So we were extremely confident that when it identified a feature, that feature was really there. What we had a problem with was that frequently it missed the features that you could see clearly, but we're very confident in our identifications out of this model. And so the key result that we got out of this that Justin just hinted at is that the atmosphere is dominated by 3 primary boundary layer states. The atmospheric boundary layer is going to be found in one of 3 conditions almost all the time. It's either a convective boundary layer, that would be the microcells, or it's a stable boundary layer, that's the no Mabel coherent structures, no imprint of the atmosphere. So everything is suppressed or convective, but there's this intermediate class that's near neutral stratification, and stratification is the key. There's often this focus on buoyancy, but buoyancy is not the important parameter in isolation. You need the competition between shear and buoyancy, and that's what stratification is. It's the ratio of the production of turbulence by buoyancy compared to that by shear. And that's the trade-off. You have a flow bifurcation. The character of the boundary layer flow changes between these 3 states. And it's important to recognize that it's 3 states. There was a recent NASA study filling in on their decadal survey, a PBL incubator study, and they were specifically told not to consider wind. Not considering wind means you can't get shear, which means you can't look at stratification. And because of that, their report states that there are 2 boundary layer states. It's either convective or stable, and that's wrong. There are 3 boundary layer states, and I think that point cannot be overemphasized. So this is kind of the summary of way too many years of research to come to this relatively simple figure here. This is the same example of cells, roles, and nothing. And we mapped that out against ERA5 stratification parameter, a bulk Richardson number that we defined. And if you look at the overall stratification, it's this gray histogram in the bottom here. And you can see it's slightly unstable, generally near neutral. It's a convective boundary layer. And then if you look, or it is what it is. It's dominated by near neutral, essentially globally at the wave mode sampling. If you look at the individual PDFs of stratification for each one of these three classes, you can see that the convective signature occurs when it's unstable. The role signature occurs when it's near neutral, and the nothing appears when it's stable. The boundary layer is suppressed. So that, I mean, that's the fundamental research. It seems relatively obvious, but this is the first global survey of atmospheric boundary layer state ever accomplished. This is groundbreaking work, I think, modestly. So this would be a map of relative occurrence of the different features. And this is at the wave mode sampling. We actually focused just on wave mode 2, which is the larger incidence angle, because it had, in our initial study of this, a higher signal to noise. So we have the distribution, the relative frequency of convection, near neutral, stable. And I think the first thing that jumps out is if you look at the tropics, you can see it's complementary between convective and near neutral, right? It's either windy or it's convective. And then if you look at the mid-latitudes, it's a little bit harder to see, but what's happening there is you're going through the baroclinic waves that are, 7-day waves that are always there in the mid-latitudes. And you're either in the warm sector, the cold sector, the occluded sector, and your boundary layer is continuously transforming between stable, convective, and near neutral. And if you focus in on just data that's poleward of the of 25 degrees, sort of the nominal mid-latitude, the default state is this blue state, the wind streaks. It's near neutral, the winds are high, the stratification is low, the flow is westerly, you have rolls, right? And then you have these advection regimes where you're cycling through the baroclinic wave. And if you've got poleward flow, that's warm advection, you're gonna tend to go stable. And if you have equatorward flow, it's cold advection, you're gonna turn more convective. And the boundary layer is bifurcating, the flow state is bifurcating, it is changing between wind streaks and cells or wind streaks and nothing. And that's as the boundary layer cycles between near neutral and either stable or unstable. And that's what's happening in the mid-latitudes. And then the other important point that I want to drive home on all of this is there's been a lot of talk about this wind streak signature and its relationship to surface wind direction. The wind streak direction actually depends on the mean shear profile throughout the entire depth of the boundary layer. And in particular, it depends on the mean shear in the crosswind direction. Boundary layer profiles are almost always turning. There's a downwind, crosswind. You almost can't have a turning profile without an inflection point in the crosswind direction. That's the dynamic instability that generates the rolls, and it's the characteristics of that plus the characteristics of the boundary layer turbulence that determine that orientation. So a long time ago, actually for my thesis, I made a prediction that the thermal wind in the boundary layer, this extra linear shear due to horizontal temperature gradients, would shift the characteristics of the boundary layer rolls. And in particular, it would induce this sinusoidal variation of the wind streak orientation relative to the surface pressure as a function of the orientation of the thermal wind. But there was no data to test that. I just, I did it. There was no way to test whether it was right or not. I just wrote it and put it out over a transom. So finally, with S1, free and open data, millions and millions of wave mode images, there was enough data to pull the signal out. And you can see that each one of those little dots on there is a wave mode image. And if you look at the horizontal dashed line, it's about a 10-degree nominal barotropic turning of the wind streaks. But you can modulate that with about 100% amplitude by a moderate thermal wind signature. So this is important to keep in mind, that the wind streak and the surface wind are related, but they don't have to point in the same direction. The dynamics that control the wind streak is the entire boundary layer profile and the turbulent characteristics of the boundary layer. So, and then this was a plot that this is fairly new. And I think Justin was being modest in saying we're not doing very well with improving the machine learning. This is our old model here. And this is a plot of true positive versus false positive. So true positive is solid, false positive is dash. And if you focus in just on the wind streaks, the blue curve, you can see that on our thresholding in the old CM wave model, it was pretty flat. So it always detected them and it was never wrong. But if you compare it against this test data set that we're looking at here, we're really only picking up a tiny fraction of the existing wind streaks. We're leaving a lot on the table. Now we have this newer model that we've been working on, really Justin and the guys at Hawaii, in which we're now picking up closer to 70% of the available wind streaks. So a factor of 5 or so improvement at the expense of a certain number of false positives. But we were leaving so many on the table, and what we really want to get at is the total count of these features in the boundary layer. And I think we're narrowing in on that. So this is just state-of-the-art boundary layer analysis. I think it is the only global boundary layer analysis data set out there. So the other thing I've been working on is trying to extract the tropical cyclone mean boundary layer structure from SAR data alone. And this is in collaboration with the IFRMIR folks. And the idea is that SAR gives you a unique, very high resolution view of the bottom of a tropical cyclone. It will tell you effectively the surface stress, and it'll also give you a surface value of the eddy viscosity. From that surface stress, I can retrieve a sea level pressure pattern, the pressure that corresponds to that set of stress vectors. And I can take gradients of that and define the gradient wind at the top of the boundary layer. So that gives me an approximation to the top of the boundary layer flow. So I have one boundary condition at the top and the boundary condition at the bottom. And then the additional piece of information we get from these new Sentinel-1 images is an accurate mapping, a reasonably accurate mapping of the orientation of these boundary layer rolls on the sea surface. And the key thing is remember, that orientation tells you something about the distribution of wind in the boundary layer and something about the distribution of eddy viscosity in the boundary layer. So that's giving you mid-boundary layer information. So the goal is to try to simultaneously retrieve the roll vortex orientation and the mean wind profiles using these two boundary conditions and a similarity model that I developed some years ago. So this is an example of Hurricane Larry from a couple of years ago. It had a nice research aircraft flight that was timed to coincide with the SAR overpass. And that's the retrieved pressure that I have there, that color picture in the left. So that's the pressure pattern that I'm retrieving from the wind vectors. And the little gray dashed lines in there are the orientation of the roll vortices. And then this plot here, this time series plot, is showing the difference between the surface pressure estimated from the aircraft flying through the storm. There are 8 storm penetrations in this flight, versus the SAR retrieval of the pressure, and they agree quite well. And then I can compare against the dropsons here, and this is the best comparison where take the pressure difference between all the possible pairs of dropsons that landed in the storm during this aircraft flight. And the key thing here is that the slope is 1-to-1, and that's all I was really looking for, is a 1-to-1 slope. But the RMS is relatively low. This is the RMS shown there is kind of a gaudy RMS. I would say the RMS is closer to 4 millibars on average, but for this particular storm, it was quite good. So these are the two input or the input conditions I give to my model. The SAR-derived gradient wind speed, top of the boundary layer, say 3-kilometer wind, and then the tangential and azimuthal components of the velocity at the surface. That's the input to the model. And you can see the wind speeds are quite high here. When you go into yellows, your hurricane force, go into oranges, your category 2 reds or category 3, et cetera. So it's quite high winds. So this shows a mapping of the observed wind streak angles on the left. So this is what we get from the SAR, and the sign convention is when it points into low pressure, it's a positive orientation. When it points outward from low pressure, it's a negative orientation. And then what I have here are two different, very reasonable approximations, a priori approximations of the eddy viscosity as a function of height that are highly typical of the parameterizations that are used currently in numerical models. And you can see that you get very, very different pictures of the orientation of the rolls using these different parameterizations. And the key thing here is that what I'm finding is that the closer I force the maximum of eddy viscosity to the surface, the better my results are, unless I push it too far. And that's consistent with very recent LES studies that are being performed. So it's on the track. This is still, very much work in progress, but I think we're getting to the point where we can start matching these two things and then start looking at the winds. So in this case here, on the upper two panels, this is one of those cross sections through the storm from the NOAA P3. And on this P3 flight, they had this fancy new downward pointing KU band Doppler radar, and it's mapping the wind profiles below the aircraft, nominally in the boundary layer. So the colorful one on the left is the azimuthal wind speed, and the red and blue is the radial flow. So when it's blue, it's inflow. This is the flow that feeds the storm, and then it turns around near the top of the boundary layer and starts pointing outwards. So the depth of the inflow layer is a little bit below the actual top of the boundary layer. And this is just one pair of SAR-derived mean wind profiles that I'm getting from this, I know to be incorrect eddy viscosity distribution. But to me, this is promising. I'm getting order of magnitude velocities in about the right place. And I'm kind of optimistic that I'll be able to do much better as this research goes on. But the important thing is that these wind profiles that I'm showing here have no information coming into them except what is derived from SAR. So if this can be turned into a processing technique, this is a whole nother level of data that could be extracted from SAR and given to forecasters or whomever is interested. And so that covers what we wanted to cover, and we wanted to open up for discussion now. Yes, please.
Thank you, Ralph, for a very nice talk. So, and Justin too. I'm curious to see for TCBL in tropical cyclone, and how do you expect of the feature of surface roughness when you have a very strong wind and you have a decrease related on the CD over 30 meters per second? So how do you, what is your expectation in terms of retrieving surface stress in
well,
from SAR?
That's an extremely good point. What I'm using here is a straight an expansion of the core drag coefficient, the core bulk flux model, and then it matches into the current expectation of the high wind behavior of the drag coefficient. What that ignores is the importance of swell and wind blowing into the waves, long waves, across waves. But from what I saw from some of the talks over the past few days, I think there's a possibility that we might be able to get some estimation from the SAR of at least the swell out in front of the storm. One feature that I've noticed a lot is that often get this outward pointing roll orientation kind of in the front left sector of the storm. And I've been kind of suspecting that's a change in the stress due to the interaction of the wind and the swell. And so I keep asking Alex and Bertrand and everybody if they can start getting estimates of the swell out there. And we might be able to make some ad hoc assumptions, add some asymmetry to the bulk flux. But for working from SAR only, then that's the goal. SAR only, no other input. That would be a very important next step. We carefully tried to leave a lot of time for discussion here.
I'll just use a big mouth. No, don't say anything. Oh, yeah. Hello? Yeah. Again, nice job, both of you guys. So Ralph, this was all done at C-band, I assume. So do you want to speculate what can L-band buy you, what can X-band buy you, and in respect to these large wind events?
I kind of I'm not really a radar interaction with surface roughness person. I'm a consumer of the output. So I need to defer to Justin, who probably knows more, or maybe Doug in the back there might know more.
Okay. Or Dr. Fab.
Oh, is he here? Doug, can you answer that question?
Not easily. Yeah, it's I suppose that with L-band, you have some possible capability to start to think about something different in terms of how you're interpreting the surface, as we talked about, once you get above 30 meters per second. I know that it's a difficult thing to think about the fact that you're working on Bragg scattering waves anymore from the SAR once you get above this, and there's so much foam and volume we're starting to think the L-band brightness temperature, for example, is some sort of a useful way to think about understanding what's happening between the backscatter and the emissivity above 30 meters per second, because the brightness temperature from the passive radiometers is going up very similarly to the cross-pole signature. And so the frequency is one aspect of the issue with providing different radar measurements, but just the basic what is the surface at that point in terms of emissivity and reflectivity is as big an issue as the frequency of the radar. Are we looking at foam now mostly? And so in terms of the wind speed that's retrieved versus the brightness temperature, I think this is like still under investigation. But I haven't worked in these high winds myself in a long time, so this is just my recollection of what's going on lately. Is the biggest thing that they're seeing is the cross pole signature is the one that's kind of working very well to go up in a nice way with the brightness temperature. And this is some sort of extra information to go with the copole. So I guess I ended up talking more about polarization and emissivity than I did frequency, Bob, but that's all I got for you.
Thanks, Doug. Appreciate it.
So, in your machine learning task, you had a gazillion imagettes that you looked at that were classified, but your number of, as you mentioned, the number of results per class was more skewed toward the boundary layer results. So, and you have like 10 classes. So was there some challenge with the classes that didn't have so many results, that they were also, you have a high confidence in those?
Some
So if
more
you're,
so
you
than
know what I mean? Am I getting it?
Yes, yeah, I understand the question. Yeah, some of the signatures are very distinct. So this means that you do not need a large training data set, for example. So things like rain cells, they're very distinct. You know, they have this really bright pattern and dark area surrounding. Probably don't need that many of those to have the model work well. And also the false positive rate is end up being really low for that class. So that's one example that works well. Other things like, well, in the original methodology that Wong did in the model, the oceanfront class was not well defined necessarily with the way that we tagged the images. And then that ended up being noisy in the model. But we think now that we corrected this with this multi-labeling idea, because previously we just said, one image, it's going to have one set of tags. That's more of like a classification of that image. But if you try to do a detection problem in machine learning, it's actually very complicated. It's more complicated because you want to pick out everything on that scene. And that's the pitch I gave to everyone too, is find everything on that scene. That's a little more complicated because even a really subtle feature, you still want to capture that it's present in that imagery.
So what was your number of training sets for let's say front? How many did you end up with?
We have, okay, so I'll just try to give a round number. I think about out of like 10,000, we probably have like 500 ocean fronts. And that's again, 10,000 just choosing a random sample. That's probably what you'd get. So it's not a very common class, but it is there. And when you see it, it is distinct and the model can pick it out pretty well.
I think Hans was first.
Justin, how do you distinguish low wind regions from rain?
Yeah, that's complicated sometimes because they have a lot of similarities. But with rain, it usually has this very bright, pronounced area that maybe Vernon can tell us exactly what that is in the imagery, but that's the definition of the rain cell. So it needs to have that. Where low wind, usually there's any feature can dominate the backscatter. So you see all kinds of random things. But what's interesting is if you look at a lot of the imagery, you end up seeing similarities in those low wind. So it actually works as a defined class, even though it's such a random class, so to speak. But if you look at collectively, say you look at 100 images of all low wind, you'll get the idea of what a low wind definition is. And the model can then pick it out pretty well if you feed that to it.
I don't think I agree with you. We looked at over 1,200 images during the Deepwater Horizon oil spill, and it became often very difficult to discern what was low wind, what was rain, and what was oil.
Mm.
Oh, I think next door to Hans was next.
X and C band.
Yeah, just in line with the machine learning, I feel there's some skepticism in the room. So I just want to kind of bring this question to all of you in a way. So where do you see like the machine learning part goes? Because it's have been like there for years. We're talking about traditional methods and then more new deep learning and UNet you have mentioned. So I wonder, what do you feel this community? Are you on this exponential rise, or you are in a winter, or there is a stagnation? Where do you see, well, machine learning is going? Are you forecasting then going to be, well, stagnation in machine learning use and criticism, and you're not going to get improvements because you don't cover the whole problem? Or what's your viewpoint? Or it's still a hype around that?
Well, just a quick quick response to that before Craig. I think we're in the baby era. I mean, we're the toddler stage of machine learning. Machine learning was developed for an entirely different, machine learning was developed to sell you stuff. And we're trying to adopt it to learn things. And our goal right now is we're just trying to get the machine learning to repeat back to us what we see when we look at the SAR image. So we're identifying the features by eye in the SAR image, and we want to try to get a computer to look at the image and see the same thing that we're doing. And we are, I think the slide I stole from Justin there shows that we're improving. It also shows we have a long way to go.
Just my thoughts on this. I mean, I think this is not a new problem that's been worked on for at least as long as I've been in oceanography. You know, we've given it different names. It's essentially just classification, so fine. I think part of a route to success here is to try to invoke more auxiliary data sets that can actually give a background context. You know, there are different satellite observations that can be used. There are model outputs that can be used, and I think that might give that missing sort of link. That will help. But I think there's always going to be the complications of nature where it will just confound any kind of classification. You know, I always remember Steve Thorpe. Remember Stephen Thorpe years ago? He brought 10 photographs of SAR data where, from the early sensors of the European Space Agency, and that's how you got the data. Then you got a nice big, you know, A1 photo, and put them out on the table, and invited all of his friends at Southampton to come and tell him what we were looking at, and each one was a PhD. And I mean, I think that's still true today. There are many processes that have a surface expression that are just beautiful, but extremely complex to understand. And I think that's where we have to be real about what we're trying to achieve here. I mean, for a given application, we may have some success, but I hear what the guys working on the Deepwater Horizon say, because it is super complicated. And we have to be very careful as well, because as soon as the newspapers discover that, you know, streaks, and, you know, we know that there are problems where all of a sudden the space agencies have been telling lies, because, you know, the oil spill up on Brittany coast. Well, look, there's all these streaks down in Portugal. That's where the real one's going on, and they're just wind streaks. So, yeah, it's a tool that we have to use. We have to constrain, but I think more background context will help a lot.
Yeah, well, what the data that we brought in to help us classify the images, or actually to relate what we classify to reality, is the ERA5 surface analysis. And we know that there are problems with it. We also know it's the best there is. And so that's what we compare against to get our stratification values at the location of the image. The point that we have is that there is, you can't rely, I think, on any other data set to really tell you the fine features of what you're seeing in the boundary layer, except for SAR. Clouds are only going to tell you things if the cloud is forming in the boundary layer. It's going to tell you only what's going on at the top of the boundary layer. Of course, SAR is only telling you what's going on at the bottom of the boundary layer, but it doesn't care if there's an intermediate cloud or no cloud at all. It's always going to give you the same answer. And what we're appealing to in this wave mode project is the wave mode is the only thing that gives almost global constant coverage. And we know we're filled with problems and filled with error, but we're hoping that if we throw 6 million, literally 6 million images at the problem, we're going to pluck out the mean response. And that's what we're going for, is trying to understand the mean response. And we're getting, I think, a very consistent picture. I mean, that first cut at maps, I was resistant to putting out any maps on this project at all because of our undercounting issue. But the relative frequency, I agreed to put out a map with that. And I think that map is incredibly informative. You look at that and you're seeing that the boundary layer is vastly different from place to place. And the tropics, because the tropics are just, you know, kind of, you know, boring in a way and exciting in others, but they're always kind of doing the same thing. You get that clear complementarity between convective and shear boundary layer. And then the mid latitude, what you're really picking out, and, you know, I showed this at the AMS meeting back in January, and I got jumped on for showing these wide swaths of stable stratification in the mid-latitudes. And she said, you know, people are going to doubt you because of that. And then I uncovered the ECMWF surface analysis on the other side of the panel, showing that EC was actually telling you at about the same frequency, the boundary layer was stable over there. So it was there, but it wasn't acknowledged. And it's where you are in the sector of the storm. That's why there's no pattern in the mid-latitude, because the mid-latitudes are just the waves going around and around. And wherever the evolution of the storm is, the size of the storm, the position of the storm at that place and time, that's what the boundary layer is going to do. But you don't get a pattern like you do in the tropics.
So I want to just reiterate what was said before, which is that you know, sometimes the rain cells look very different, and in particular, they look different at L band than they do at C band. And I was wondering what your plans are for training with an L band data set instead of only Sentinel, because we're going to have NISAR data. pretty
NISAR is
soon.
getting nothing over the ocean.
That is not true.
No, they're only going to get a few seconds going on and offshore. You get about 50 to 75 kilometers. I've talked with the head NASA guy at NISAR, and he has made it very, very clear to me that there's going to be nothing going. He wasn't even interested in trying to capture tropical cyclones. He said that, you know, all our bandwidth is consumed with the applications for which we designed the instrument.
Well, now you're talking to me.
Okay.
There is going to be acquisitions 100% of the time over the Gulf of Mexico.
Yeah,
and
over the
Caribbean
Gulf. Yeah,
Sea.
yeah.
And we're now looking at getting some data off of the east coast of the US out to about 600 kilometers.
Okay, so this is different from the last time I talked to talked to him. Yeah.
Gerald is very
But
negative.
I knew, yeah, I misspoke because I knew that the Gulf was going to be covered. And so that'll be very interesting to look at what's going on in the Gulf. But, you know, the Gulf is always, you know, pretty much tropical-like. And so, you know, that's the kind of behavior we'll be able to get the comparisons between.
I also want to point out that one of the things that could come out of this workshop is a recommendation for super sites where, you know, we go and say, you know, SAR coordination efforts are being put forward to have super sites over these areas. And it's true that we're not going to be acquiring much in the polar north, but there are other sites that could be used.
So there will be some routine collection out to about 600 kilometers?
We are not, we are in the negotiation stage for
Okay.
that. But it's not.
Because
totally-
how I understood it was to accommodate anything over the ocean, he had to subtract from somebody's overland application.
And that's the negotiation.
Okay. And then Bjorn had a question.
Yeah.
Hello, test. Test.
Okay, okay, thanks.
Okay. Actually,
Thanks,
I want to pick up to the person we were talking before you, Kathleen, who also wants the microphone again. Because I totally agree about this auxiliary data, which is required, especially when I hear about the discussion now with the deep water, horizon hole spill, rain cells, and wind. And what you said, Ralph, that the purpose actually was of this multi-classification problem to teach a machine learning system to learn that what a human being is able to see on the images. But I would suggest here to drive this a bit further. So when we have information of the ground available, then in my opinion, machine learning is able to see even more than a human being is able to see. So when we start training a machine learning system on features because we have the ground truth available, then we might be able to get even more out of the SAR data than a human expert would be able. And I don't know if this was a joke when you said there's a competition on investigating those images, Because then I wonder, how do you want to find out if who is right? Yeah, you have maybe a board of experts who have an opinion of some feature, and then you have the one who is tested and taking place in the competition. But you never know if so. Science is not democratic. So even when the board is voting for one thing and the other expert is voting for another thing, when you don't have the ground truth, you never know who is right. So it's I think very important to have the ground truth available, and then maybe a machine learning system is easily able to distinguish between oil and
Yeah.
wind and rain cells, although a human being has really problems in doing this.
Yeah, those are all very fair points across the board. The point is there is no ground truth for boundary layer state. There is none. And the other issue is yes, we're hoping that the machine learning can pick up things we miss. But I think before we go for things that we don't know about and can't see, let's at least try to reproduce what we can see. I mean, I think we don't want to get out in front of our skis. We got to stay where we can be relatively sure. And as far as the judging on the contest goes, remember, this is for a t-shirt at best, and bragging rights. But we, between the three of us and other people who have worked with us on classifying these images, we've learned how to assess consensus in the state of the image. And we'll be probably applying that same methodology to this.
So
There's a question online too.
Oh, okay.
You do, thanks.
yeah, it's
Okay.
okay. It's on.
I can't read it.
So thanks, thanks, Ralph and Justin. I want to go back to this issue now, that what you have demonstrated is really nice from the global perspectives, as well as for some of your selected images examples. But the sensor synergy now is an issue that you could invoke into this classification as well. It would indeed help you on frontal detection, where you are a little bit sort of unclear whether this is to be classified as a front or not. If you had a good example from other optical or microwave type of observations, you could sort of invoke that into the decision process. And this becomes an issue that then becomes more of a thing you don't want to necessarily do globally, but if you had the super sites, you could benefit from this. And the SynTool platform illustrates this over and over again. Hence, it is also a fundamental kind of playground tool to be ready to just take the new satellite mission data immediately onto the analysis scheme and invoke them into this multi-sensor kind of classification approach. So I really like what you are doing, and I think it's worth building this, extending this into the synergy at SuperSites.
Yeah, I mean, certainly. We've actually had lots of internal debates about what we call ancillary information, feeding it in, and Justin kind of appreciates the arguments one way or the other on whether or not to include it.
Yeah, we've been trying to look at that. In other words, use like combine basically the features you see on the imagery with other input. And we started using parameters to start. I mean, well, with the boundary layer stratification issue, really what we're capturing is basically the temperature differential compared to what other sensors cannot see. So now if you couple that, for example, with SST, which we know very well from other technologies, radiometers, you can now constrain the problem better. And now you add in the scat winds that have a very good ability to get U10. Now you can constrain the problem more. So all these different things of inputting this, and actually Ralph didn't talk about that, but we were very, put a lot of thought in how we calculated the Richardson number. And we tried to use parameters that are easily, or we have a good handle on from other satellite technologies. with that in mind, actually moving forward to synergy of the problem.
And in fact, the marketing of the proposal that we sold to NASA was providing information that would help them constrain delta T for heat flux retrieval, because that's their big issue right now, is trying to get the air-sea temperature difference in order to get the fluxes over the ocean. And it's an incredibly hard problem to separate the effectively 10-meter temperature from the sea surface temperature. And our thought was that if we could provide you information about the stratification and at least constrain the stratification somewhat, then your chances of retrieving the 10-meter temperature hopefully improve. We didn't say we would do that part of it. We said we would produce this information that some smarter person could use. And in fact, Justin and his grad student produced a model to going straight to Richardson number from SAR imagery at various levels of ancillary data. And you can explain that.
Yeah, I think it was just preliminary work, but it shows that the information is in the SAR. I don't think our model was the best in terms of operations, but it did show promise. Is there any other point? There's a question online. Maybe I'll
just one quick comment first, which is trying to bring some of this together. I mean, we will have Roselle also as a useful sensor coming in 2028 in L-band, so that will give us some nice capability. And there you'll have the tandem sort of configuration between Roselle, L-band, and Sentinel-1 C-band. So that's going to be quite useful for this. I think also we have several other tools that we've been using for different things. One is the SIN tool and the work that we've been doing with the Ocean Virtual Laboratory. That's very helpful to try and get to grips with these complex situations, because most of the time we're dealing with quite complicated configurations when you're looking at the different streets and the atmosphere. Then you can go into all sorts of different kinds of convection, open cell, closed cell convection, etc. We also have a system called the Multi-Matchup Dataset, MMS, where we're combining different data sets in order to do validation. So in sea surface temperature, we do the same thing, where we're bringing different data sets to bear on the validation problem, because we know that if we're trying to validate using drifting buoys in strong sea states, we don't get a good result. So we can stratify that out. But that can also be used in the same kind of game that you guys are playing here. So I think that, trying to bring tools together that allow us to very easily inject data for multiple purposes is a key way forward here. So that's something we might think about, because those kind of tools, especially in today's open online computing infrastructures, can have multiple users doing multiple things, and you're maximizing the collaboration and the amount of data that you can bring to bear on the problems. And it's quite trivial in a certain way to add classifiers on top of that afterwards.
We'll just go with the question online first. I think add Stuffle in here. Let me go back. So this is for Ralph. How do you verify streak and wind direction? I'm getting worried when you say you use ERA 5. Perhaps I missed this in your talk.
I'm not sure I quite understand the question, but the idea is that the direction of the wind streaks does not necessarily follow the direction of the surface wind. The direction of the surface of the wind streak is determined by the entirety of the boundary layer wind profile from the surface to the top of the boundary layer, plus the effective eddy viscosity distribution within the boundary layer. And so that's why the wind streaks are giving you information about more than just what's going on in the surface. They're actually telling you a little bit, implicitly, they're telling you a little bit about the vertical distribution of eddy viscosity, and they're telling you implicitly a little bit about the distribution of shear within the boundary layer. And the goal is to try, it's an optimization problem, to find the most reasonable fit of wind profile and eddy viscosity profile that will match all of the information we extract from the SAR. And so this is extremely preliminary work, but even just playing around with parametric eddy viscosity distributions I think I'm getting, to me, getting this much structure right on essentially the first stab at the problem shows to me that there's a lot of promise in this. And it's all constrained on dynamics on my simple model of how the boundary layer wind profiles look in the tropical cyclone. Just as long as I got this figure up here, I wanted to draw attention to something that's in the IRAP data. And I put it up there so that people could stare at it. But if you look at that wind, you see it's defining a mean. But if you look really carefully at it, you can see a periodic modulation of that wind. And you can imagine that the wavelengths of that you would project into the actual orientation, that's kilometer scale modulation, and it's extending up through the boundary layer into the supergradient wind area there. And that's exactly what the boundary layer rolls do, is they add an additional momentum transport from the boundary layer that's not diffusive, not associated with the eddy viscosity. It's an advective transport of momentum, and the rolls are grabbing that supergradient momentum and trying to sink it into the ocean. And so we're now getting conventional observations that can give us means and perturbations. And we can compare that against what we can extract from SAR. So I think.
Yeah.
Yes, if I can intervene with my voice because my question was not so clear apparently. I fully appreciate the theory, of course, Ralph. We discussed this many times before, and I really appreciate it. My question is related to the last sentence, which is the verification. And of course, you know that we have been comparing buoys and spectrometers and models, and also I presented this the long-standing problems with wind direction in models. So I think in the context of the wave imagettes, you talked about the verification with error 5. Then of course error 5 has these systematic direction biases. So I wonder what other tools did you also look at more buoys to understand the role and the wind direction differences, or?
No, actually we recognize the errors in wind direction from ERA 5, and we're throwing the law of large numbers at it. But one thing I would say is that when I look, if I remember right, your difference maps between scatterometer and ECMWF, they're sort of like first forecast hour or something like that. So after the assimilation is sort of washed away as it will, and the model doing what it wants to do versus what the scatterometer is saying is actually happening. That was a question.
So no, we also, I think that's another question. So we verify with the first guess to not be dependent on the spectrometer data estimation, which we also tested. So indeed, the spectrometer information is washed away in the first hours. We actually recently also verified an experiment from ECMWF not using any spectrometer data, and the difference in the biases in the first guess is really minimal, like maybe 10%. So we know that our assumption that the model is doing its own thing dynamically is correct. And also, of course, the spectrometer data are not able to correct the analysis everywhere, only in some places where there is spectrometer data. So also the analysis is extremely bad, actually, the error 5 analysis, because it's confusing areas with spectrometer data with areas without spectrometer data, presenting you different characteristics of the boundary layer.
Yeah. We recognize all the problems with ERA 5, but we still think it represents the best available product. But I mean, what I see from our plots of boundary layer state change, having a pattern somewhat similar to your difference maps between the scatterometer and ECMWF are suggesting to me that the boundary layer parameterization in ECMWF is not properly capturing the bifurcation in what the boundary layer should be doing as a function of whether or not there are specific types of coherent structures present. Because I know that it runs some sort of a EDMF-like model, so it has a somewhat idealized ED model, and then the MF is just purely for convection, but I don't think the MF even includes momentum, does it?
Well, I can tell you that the ECBF just switched off convection, and then the wind direction biases disappear. But of course, that's also not correct to switch off convection.
Yeah. So I mean, to
So
me,
indeed,
what those maps are
it points-
showing
it points
the
to
error in the.
correct indeed.
Okay.
Yeah.
So I think there's another question from the audience, Roman.
Thank you, guys. I have, let's say, two comments and question. You were talking about the with respect to the question, with respect to the low wind, the oil slicks, and the rain cell. Of course, I guess it goes back to how you decide to define the classes that you have set. Of course, you can have low winds by caused by a rain cell or next to atmospheric front. So that has to do with the fact that you are seeing or not a rain cell, and maybe that has to do also with the size of your image. So very nicely you showed the improvement that you got from following the increased size of the imagejet. So I wonder whether you would have some recommendations for the future missions with respect to, I don't know, maybe even bigger imagejets, or also maybe a single mode, because I think the beauty of what you're doing is that this is systematical. And let's say that with respect to Johnny was saying, your super site is global. You don't need any super sites actually, because I think it's very nice that you're showing something global to global scale. So having, some people talk about Sentinel-1 next generation having or after having a single mode used everywhere. So maybe that could help also applying what you're doing in both the offshore and the coastal regions to apply that systematicity that you're doing. And just going back to the fact that you're defining the classes yourself, have you been thinking or trying to do unsupervised learning of all the features that the wave mode is providing?
Yeah, so the multi-part questions and comments there. I'll try to address each one. The first comment about definition, and I think that was what my response was to Hans, was that if you define a rain cell as having this bright structure with dark area, the machine can pick that out pretty well if you train it like that. But that does not say that there's not rain in the image. And that's more complicated. That's why you're going to need these, whatever, auxiliary data, especially if you're next to like near land and you have one of the NextRack systems. That's a great way. And I believe your group maybe has done some of that too, where you can actually get rain rates out of it. So that's really promising. But I just wanted to specify that if you tell the model to find a certain very distinct thing of a rain cell, it actually picks it out pretty well. So the next comment about future missions, I think that was, or
the recommendations that you would have maybe to help doing such type of work in the future. What there were some comments about additional polarimetry, additional band, or any comments on the geometry?
Yeah, maybe I'll start with that, and Ralph can jump in if he wants. But so for the boundary layer type things that we're seeing that are everywhere on the imagery, sometimes the 20 kilometers is just a little bit too small, and we cannot see what. But also these the turbulence really scales with the boundary layer height. So we're talking about 3, maybe max 5 kilometers or something.
Or
So
larger, yeah.
or a little bit longer. So we might need a little bit bigger images. I don't know how much, maybe 30, 40. That's
Biggest they'll do.
hard to say, but we do have IW, which we can learn from a lot. The other thing that I haven't really heard talked about much at the meeting so far is that there's a private industry kind of booming, right, with a lot of SAR systems. I think this is something that we I mean, I guess we're, to quote Bertram Chaperon, you're a rich guy, you're rich, you have many data. And he always used to say that with Sentinel, and he's right. So I guess we haven't needed to look at these data as a community because we have so much Sentinel data. But with the private sector, they have a lot of different modes and features and frequencies that maybe we can take an advantage of to plan for next missions. So that's maybe something we could talk about as a community. I mean, there's ISI now, Capella. There's probably other ones, but those are the two I know of offhand that have a lot of different features we could take advantage of to see how they would maybe increase your signal to noise ratio with some processes. So-
Yeah, the only other thing I would add to that is maybe a larger incidence angle. We found the signal to noise on retrieving atmospheric features improved with incidence angle. The wave mode 2 was roughly twice as good as wave mode 1. So, would it be better if there was wave mode 3? I don't know. We hope so.
Yeah, let's expand on. Yeah, that's a great comment about, and we'll ignore Ralph's comment about free SAR for the people. But that'll be solved. But in your neural nets, I'm not hearing enough when and where. And for example, when I give people, what is this image? I at least give them a fighting chance. I say, here is the lat longe and here's the time it was collected. So you can maybe use some of your oceanographic knowledge, if you paid attention in the early days. But where I'm really going is when and where and varying the imaging parameters can also really help you with your AI work. And we get asked all the time by sponsors in the US, frankly, DARPA, what the hell, here you guys at IRM, we're the new IRM. What would you do with small sats? Why are they better? And I think the short answer is revisit time. And we exploit time all the time now. Our wetlands projects at L-band and the Laurentian Great Lakes, it's all done with multi images collected over time in comparing the evolution of the inundation of the water. I'd argue with fronts, I want thermal like Yanni or chlorophyll maps, but if I can't get them, I just look at a SAR image every 3 hours from eyesight, for example, and that's going to give us a tremendous amount of knowledge on separating out what is that feature and what is the driver for that feature. So again, as we talk about, synergy can be defined multi-frequency, multipolarization, but synergy can also be, hey, you have 10 SARs up there, just stack them on top of each other and use that time as your weapon to do a better job. But anyway, so I agree with your comment.
Yeah, I mean, we're definitely, I mean, our sampling is, morning, night, right? At 6 a.m., 18. And we're missing the whole diurnal cycle. And we can see the diurnal cycle just in the difference between morning and night. I mean, in the tropics, what we found near Barbados is that the stratification was roughly the same between the morning and nighttime passes. But how you got at that stratification was very, very different. You had compensating change between delta T and wind speed, and they were almost canceling each other. So the stratification was staying at those two sample times the same, but it was getting there from two different paths. One was more buoyant and one was more sheer, but you landed at the same ratio. And Doug, I think.
Yeah, I just wanted to make the comment. I don't know if it was totally clear if everyone knows what the wave mode, imagejet mode is on Sentinel-1, but if you don't and you're interested, I think that's an important thing. It sort of flipped for us everything on its head from going from looking at the SAR images with all of their rich features in a wide swath mode and trying to understand that image, as Craig said, to having millions of small images where we didn't know when and where necessarily. And we just scratched the surface of using these data for the atmospheric boundary layer. We took one particular topic, but there is so much that can be done with these images that we're not touching. And it allows you to bring everything you know about SAR, if you're a SAR expert, into the mix with the constraint that you just have these couple of incidence angles and one frequency right now. But it also maybe gives you the opportunity to look forward to the idea of what you would do, as Roman said, with the next SAR that you're building, because it just opened our eyes in a very different way to trying to use the SAR images and just their texture. And I'd put in a plug on the Richardson number side. There was a recent master's at Ifremer inverting the Obakov length with just the basic idea of doing the neural net directly to an observable as well. So there's a couple of attempts to do this other way rather than trying to classify the images. And so I just wanted to make a plug that there's lots of opportunity in the wave mode. And one other point I wanted to make is, as Ralph said, for the atmospheric stuff, you really need short waves that are very ephemeral. So I don't think you're going to see them in L-band, but you're going to see them in SWAT, the K-band SWAT, I think. And so very soon, I think we're going to start seeing images of this in a swath mode coming out of SWAT. And so it's another opportunity and another synergy between SAR and SWAT, I think, coming along with Sentinel that I expect is going to be there.
The other, just, expanding on the whole point of wave mode, the key thing about wave mode, if you look at the distribution of SAR images over the ocean from pick your satellite available to us, Sentinel-1, RadarSat, et cetera, you are not covering the globe like that. You're not getting an image roughly everywhere. And wave mode, it's just this mode that's producing data over the ocean. We were told it was to keep the radar from cooling off between land. And so they justified it on, retrieving waves and whatever, but I don't know if anything ever really came of that. But as they gradually increased the image size and the image quality, all of a sudden this whole new use came out. But you're not gonna cover the globe with unless you dedicate a SAR to the ocean. You're not going to cover the globe.
So yeah, I mean, with Roselle, I pushed very hard to have 100% duty cycle, but a duty cycle for a SAR is tricky. The wave mode is the response to trying to get a really good duty cycle, and it's to keep the SAR warm, ready for use. But that's what it is.
Yeah.
My point here is really building on what Doug said. We're in an ocean, a global ocean of data. Copernicus has revolutionized everything we think about. And first of all, thank you for noting that, the open policy of data is important. It is important, but it comes with some challenges. And the challenge is quite simple now. We have so much data, it starts to become a little bit troublesome. At the European Space Agency, we're trying to move now towards an open platform for the ground segment, building on the kind of work that the numerical weather prediction community has, which is you have an operational ground processor, and then you have a parallel suite, which is used to test new ideas. This will all be open. The data will be open. The algorithms will be open. The collaboration will be open. And I think, as Doug says, the wave modes have been a bit underexploited. It's a bit messy to start with, but once you get your head around it, I mean, it's a beautiful data set. It really is. But there is so much more. And I think this is one of the biggest challenges that we have. We have to, this community is not too bad. I mean, in my job, I have the ocean color, the sea surface temperature, the wind community, we have the gravity community. This community is quite good because it is prepared to look into the oceanography, and it's prepared to look at other data sets to try to get a handle on what the SAR is seeing and trying to interpret that. I mean, at the end of the day, we just have the surface expression of the full complex system. But other communities aren't like that. They get very attached to their sensor, and they can't move, and we don't see much evolution at all. So I can only encourage you to go into the wealth of information that we have. It's all open and free, and try to do as much as we can. But for that, we need the next generation of tools. They need to be online. They need to be shared. The Ocean Virtual Laboratory is one example. The multi-matchup data sets is another. The stuff you're doing is another. Yeah. But somehow we need to actually bring this together, otherwise we're just going to get lost in the sea of data.
I mean, we use Dr. Fab's site to try and figure out what's going on. NASA has got a push to try to integrate all their DACs so that they can talk to each other and combine data from multiple. They have different DACs for different data type products, but they're trying to improve that communication so that you can combine scatterometer, clouds, SST, et cetera, and have it all in one place for you, one-stop shopping with what they envision as cloud computing. So you don't have to download the data sets. You just do all your computation at the DAC and bring back the result.
I just have one comment too on Craig's is that, I mean, this is a lot of data that needs to be crunched now. I mean, the wave mode alone, I think it's probably like something like 700 or 800 terabytes, I guess, and you have to crunch it. That was and growing every minute. So this is a huge amount of data. That's why you need these tools. I mean, you need machine learning to sort through this type of stuff. And that's not even the IW. The IW, I mean, that's probably like, what, a petabyte now? I mean, it's huge amounts of data that are coming in from Sentinel.
Are you again?
Yeah. No, I mean, that's why we built the Ocean Virtual Laboratory. We were lost. We couldn't see the wood for the trees anymore because it was just too much. And we took an executive decision to say, okay, if you really want to number crunch, you need to go get the products and you need to download them. You need to work with them professionally and properly. But first of all, you need to discover what the hell you want out of this vast ocean of data. And that's why the OVL is there as a quick scroll, point and click, and look visually. Then you can go get the data that's relevant.
Yeah.
And I think the approach has proved very successful, but it's a starting point. I mean, we can go to the end of the universe with it if we had the money, time, and effort. And maybe we will one day. But today, getting feedback from communities that say, exactly as you're doing here, this is something we want to do. And then we can start to think about how to put money behind that to help.
Yeah, I mean, you're preaching to the choir in that. I mean, we're big fans of.
Especially for the money.
And even building on Doug's comment, I mean, each of these classes is its own unique set of challenges in geophysics associated with that. But at least with the classification tool, you can easily collect, give me 10,000 images of rain cells, or you can do that. So I think that's an important step with whatever geophysics you'd like to do. Sorry.
When you look at this kind of plot, you may have addressed it, but then I missed it, or at least you probably have thought about it. But to me, it immediately triggers my interest in terms of what is the seasonal variability here. Do you have enough data on it already? Or do we need to wait another couple of years with Sentinel before we have it? But it's clear in my inspiration seeing this, I would at least expect that like the wind streaks signals would potentially have quite a strong seasonal.
And they should have an El Nino cycle too.
Yeah.
But yeah, I mean, we actually made some stabs at it, but I think right now, because of the current classifier that we were using is leaving too much on the table. Our data volume is going to go up by an order of magnitude on using the new classifying model that Justin and his colleagues are developing, and the data is going to explode. And we did. I don't know if we put it in the paper or not in the supplementary. Any seasonal. No. Okay. Anyway, we just, amongst ourselves, we kind of played around with that. But the data counts were kind of low.
Yeah, just circling back to this issue of data and where people are doing their processing in terms of methods and techniques. I don't know because I'm not hearing where you're all doing your processing. But to echo what was just said, it exists in the States, and certainly Europe's put a lot of money into platforms to bring the processing to the data. So nobody should be downloading data ever.
Yeah, that's the new NASA paradigm, actually.
And I represent one of those platforms, which admittedly is focused on polar, not oceans worldwide, but the concepts are the same. And just to shoehorn in an idea that I'm currently worrying about, which I haven't heard mentioned at all, is the Commission, and by extension, the European Space Agency, are really fixated on this idea of digital twins. And it's probably a new buzzword, but it comes with lots of funding. So this room seems to be full of people who are really experts at using data, big data, modeling. Are you worrying about digital twins? Are you contributing to digital twins? Are you interested in digital twins?
Justin?
No, can you define it maybe?
It's, there may be people here better able to define it. It's a hazy concept, but it's the idea that you take everything that's being done here and in a computer create a so-called twin of the Earth, so that rather than going out and looking at the real world and finding out what it's doing, you can look at the computer and make forecasts. And by the hope is that we can get to a point, and frankly, I don't think the models are there yet, but that policymakers or decision makers can go in and do what if scenarios. And what if they don't pass the appropriate laws, what's going to happen to the Earth?
We're not, you know, that's
Yeah,
so,
okay.
that's so far beyond what we could, I mean, you can tell how noisy all of our results are. And to go beyond that, I don't foresee it in the near future.
In Europe, if you want money, you've got to somehow tie it to a digital twin, is the
Okay.
reality at the moment.
But your point is taken about doing the process, that the DACs are trying to get the DACs talking to each other, sharing data across, doing all the processing on the cloud, and then just bringing back the result. That's because they just can't keep up with, it would cost them too much to support the downloading. So they have to find some way to not download and have the data out there on the cloud. And I don't understand how this cloud computing works, but they have buckets and they pour into buckets and they spill the buckets on the side, and I don't know what they do.
So thank you all. It's 10:17, coffee is served outside, so we will reconvene here again 10:35.